Alright, hell yeah. So we have dynamics, and what we're going to do is derivatives. And so I'm going to do hopefully quite a few of these problems using derivatives. And so what we have here is, a ladder or a stick or whatever, but we have this point that's moving at a constant velocity of 1.2 feet per second. And for this problem, I'm just going to choose an angle of 30, kind of to set it up. Alright, sweet. And then so what we know from trigonometry is if we have this angle, a few things, you could put the sun is shining on the sinin, so then the sine of this angle is going to be the opposite side over the hypotenuse. So it's going to be 2 over, I'm just going to call this L for now. And hey, you could solve for L. We know what this is, we know what 2 is, and so we could just say, hey, L is 2 divided by sine of 30. And that's going to give us 4, because sine of 30 is a half, and then we get 4. So we got 4 feet there. And then, from an engineering perspective, let's say you were just given 4 feet here, and you wanted to know this height, and you knew this was angle was 30. What we know about sines and cosines, like this is the sine component, this is the cosine component of this hypotenuse, and it's the percentage. So this, the sine of the angle, is the percentage of that hypotenuse. And so that's kind of the easier way. If I'm already given the larger number, I'm going to say this is the larger number. Heck yeah, the sine of 30 is going to be 0.5. And so that's going to be basically 50% of the hypotenuse. So you would write it like L sine 30. So this is kind of the format that you would see it. If I wanted to know this side, I would do L cosine 30. And we can do that for this side, and that's going to be 4 feet cosine of 30, and cosine of 30 is 0.886. So we're going to have 4 times cosine 30, and this is going to be 3.464. Now it's also good to get used to the square, what is this as a cubed root? That'll come up quite a bit, because this 0.866, this is kind of an interesting one, because anytime you're dealing with triangles, also bring up Pythagorean's theorem, because I'm just going to call this x. So we're going to say like 2 squared plus x squared, square root that is L. That's going to be the hypotenuse. Alright, sweet. And but because you can, like in statics, you usually have like vectors. Hey, this is a vector, maybe it's 10, and it's in this direction of 30. Well, you can always make a unit vector of just 1. So it's only going to have 1, and it's still going to have an angle of 30. So we're going to blow that up. So basically, even though this triangle is 4, we can still say, hey, it's the same triangle. But now we're just going to call this 1. Like that is kind of the principle of using a unit vector. And then you would, so 1 is your larger number, 1 is your hypotenuse. We're going to say this angle is 30. And so this side is going to be sine 30. Sine of 30, and that's going to equal 0.5. Kind of that 50%. Now, this side still is L sine 30, but just our L is equal to 1 in this case, and then so you can just kind of ignore that and just know that this side is sine 30, therefore this sine is cosine 30. Kind of L cosine 30, but L is 1, so that's kind of where that comes from. Okay, so let's draw this triangle again. You're like, oh, okay, so I have sine of this angle here, cosine of this angle here. I'm going to draw it one more time, just not to confuse, not to put too many letters in it, but we're just going to do sine 30, cosine 30. We'll do it one more time too, We're going to have 0.5, and we said this was 0.866, and, I lost it, man. Yeah, 0.866, sorry, that was a typo there. Cool. And then I'm just gonna go over where this comes from. And so this is going to be a 30-degree angle. And this is 1. So Pythagorean's theorem says 0.866 squared plus 0.5 squared is equal to 1. Cool. But let's ignore that for a second. Let's say we just didn't know what this side was. We're going to bring it back to x, and this is 0.5, and this is 1. We know a 30-degree triangle that this side is a half, and this side is 1. And it's just kind of cool that you have this relationship with triangles. You know, it just happens to be that a 30-degree angle is going to cause this length to be half. Didn't have to be that way. I actually honestly don't know particularly why it's 30 degrees. You know, you have a circle that's divvied up into 6 60 degrees, so it would be 12 30 degrees. And yeah, just for whatever reason, this height right here on all of those is just half of the radius. Anyway, I'm sure there is some sort of proof there, because this is the only one that kind of really is a nice number. But also, what we're going to find out is that 60 degrees is also a nice number, because this turns out to be 0.5. And so we kind of know those two fairly well. And I guess we know 45 as the square root of 2, 1 divided by the square root of 2. That's going to be 0.707. All right, but let's focus on this. So, so if we go back to here, we're going to say that x squared plus 1/2 squared square root that is equal to 1. Cool. So now we can solve for x, or I think the simplest way, before we get too complicated, hey, what's 1/2 squared? That's going to be a quarter. Write it like this, you got 0.25. And then this other side squared has to equal 0.75. Okay, so then we can get into the game of like, what squared? What squared is equal to 0.75? Okay, well, let's write that. What squared is equal to 0.75? Well, let's take the square root of this. We'll get what? Square root of this. So that what is going to be the square root of 0.75. Now, it doesn't seem like you can do much with this, but turn it into a fraction, and you got 3/4. Hell yeah. And then just from the math perspective, even this, sometimes you kind of lose your brain because you haven't done this in a while. Well, you can always, anytime you have a quotient or a product, whether it's 3 times 4, square root of that would be the square root of 12, you know, and then you would take the square root of 3 times square root of 4, and this would go square root of 3, square root of 4. This would go square root of 3 times 2. So we can do the same thing with products like that, even with quotients. So we got square root of 3 divided by the square root of 4. That's going to be the square root of 3. And then, heck yeah, square root of 4 is 2. So booyah, this is going to be square root of 3 divided by 2. We throw that into our calculator, square root of 3 divided by square root 3 divided by 2, we get that 0.866. Alright, so hell yeah, so that's kind of where that comes from. Alright, booyah, so let's grab a new sheet of paper, and what we're going to start doing is we're going to ignore that that's 2 feet, we're going to call this h. We're going to call this x. And then we're going to call this theta, but just keep in mind that we're going to reference at theta is equal to 30 degrees, because this triangle is about 30. And then, so other relations that we want to know, well, I don't even know if we actually found x from this. You know, so I guess we can keep in mind that x is 2 feet. If you just wanted to find x, let's say you didn't want to find the hypotenuse, do we have enough information? You always have enough information if you know 2 sides of a right triangle, or an angle and a side. You just need to know 2 things, you know what I mean? So it's either one of those. There's 3 sides and an angle, and you need to know 2 things. And I think when it comes to trigonometry, it's just like, it seems like there's way too much, but it's just fascinating that, you know, just saying things like that. Well, okay, there's only 4 things, and if you know 2 of them, you know everything about this triangle. Cool. And I guess it's, you know, well, anyway. Alright, so hell yeah. If this is the angle, we can take tangent of the angle. What that says is, and let's spell it out. Tangent is, anytime you ever forget what the hell tangent is, just definitely try to remember that it's sine over cosine. I think you can remember that, because maybe sine, I don't know, sine is like the first one you learn, maybe cosine is the second. Sometimes you'll use cotangent. It's just flipping this upside down. Cosine goes on top, sine goes on the bottom. Okay, and now let's remember what sine was. And yeah, let's go through this. Sine, for a unit triangle, was just this side. You know what I mean? Okay, that was sine, and then this was cosine. Here's the angle. Sun is shining on the sine. Now, tangent is also, it's a ratio between this side and that side. So it's also just h divided by x. And let's call this L. And again, what did we say? If we know this larger number, the hypotenuse, and we want to find this, we're going to take L sine theta. So that's going to equal h. And then this x is going to be the hypotenuse, but then cosine of this angle. Cosine of the angle is the percentage of this larger number. So we're going to have L cosine theta. And this is where you can see that the L's cancel, and you're basically just left with just the sine divided by cosine. It's the percentage of this larger number, whatever that is. So you can just see, and sometimes I do this, it's just like, well, hell yeah, look at this, divided in 2. And then can't you see that that length is about that length? It's not. Visually, you can instantly see that this length is a little bit shorter than that length, so this is not a 30-degree triangle. A 30-degree triangle would be like about here. Then you'd split it. So also, this is just a quick way visually to look in problems if they're, they're usually not drawn 100% to scale. They're just kind of thrown together. Okay, but tangent is the percentage, so we're going to call this, hey, this is about 50% divided by this. If this is 100% of this whole thing, this looks like about 80%, and it's going to be 86.6% for this problem. So for sure, tangent is going to be, for this, is going to be either 50% divided by 86.6, or it's just going to be that 0.5 divided by 0.866. That sine theta divided by cosine theta. And even this we could probably just do in our head. Okay, if it was 0.866 divided by 0.866, that would equal 1, but this is a little bit less. It's not half. If it was 0.433 divided by 0.866, we'd have a half, or 0.5. So we're somewhere in between 0.5 and 1. Maybe 0.5. Well, actually, maybe it's 0.6. So that'd be a good reference. And then I would always guess like this, because that gets you closer. Because the second I said 0.6, is like, oh, hell yeah, I've come across this one before. It's 0.557. And we already know now that the square root, let's say we forgot, like, oh, I forgot what that was. But isn't it just square root of 3, the square root of that? And why would it be this? Because this number squared is equal to 0.75, and then we would add it to 0.5 squared, which is 0.25, and that equals 1. So anytime you're working with triangles, just always go back to Pythagorean's theorem, and that'll be real useful. All right, hell yeah. So then we can do this fraction. It's going to be 1/2 divided by, and we're saying that's this is square root of 3 divided by the square root of 3/4, which is the square root of 3 divided by 2. So let's do that. Square root of 3 divided by 2. That's the same thing as 1/2, and then flipping this upside down, which would be, oh, sorry about that. But 2's cancel, and then we got 1 divided by the square root of 3. And then also, just know what the hell the square root of 3 is as a decimal. Square root of 2, definitely know that one. 1.4142. I mean, you can't go wrong there. But square root of 3, I don't know. Sometimes I mess it up. It's at least 1.7. And then is it 1.72 or is it 1.73? I think it's 1.723, but 1.723. Let's check it out. 1 square root of 3. 1.732. Yeah, so my bad. Yeah, so 1.732. It's got a 0 after it, so you're pretty, if you can remember that to 3 digits, that's hella. Okay, hell yeah. So this is going to be the square root of 3 divided by 2. So 1 divided by 7, 3, 5. Oh, and what did we say? What did we say this was? That was going to be, yeah, right here. Square root of 3 divided by 2. And I thought it was 0.557. Square root of 3 divided by 2. That's going to be, and we can do this one in our head. 1.6, divide that by 2, that's 0.8. Oh, so maybe we are off. What the hell is this divided by 2? No, I don't know where. Oh, my bad. No, I messed up on my fraction. But 0.5 divided by 0.866 is 0.557. I just don't know why I'm messing that up. So we have 1/2 divided by this is the square root of 3/4, which is 1/2 divided by the square root of 3 divided by 2, which is 1/2 2 square roots of 3. It's 1 divided by the square root of 3. Yeah, okay, there we go. Oh, my bad. It's the inverse of this. So we have 1 divided by 1.732. If it was 1 divided by 2, that would be 1/2. You know, so that's an easy way to do it. If it's 1 divided by 1, it's 1. So it's somewhere in between 1 and 0.5. Yeah, I don't know. Inversing number is kind of tricky. But all right, so hell yeah. So that's going to be the tangent of this angle is going to be 0.557. All right, hell yeah. So this will be important because we have a triangle and we got 4 things going on. You have two of these sides, a hypotenuse. There's 3 sides in one angle. And if you change any one of these things, if you change the angle, you're going to change all the sides. Or never mind. But yeah, if you change. All right, hell yeah, I misspoke, and this is what I was wanting to tackle. So we have sine theta, sine of the angle. We have cosine of the angle. We have tangent of the angle. And basically, we only have these 3. The others are just... Okay, let's talk about what these are. Because obviously you have the inverse of sine, that's cosecant, secant, and cotangent. Those are the inverse. But anyway, so what do we have here? For sine and cosine, we said they're percentages, of the hypotenuse. But to make it consistent, this is a ratio. So this is an angle. So you have sine of an angle is equal to a ratio. Cosine of an angle is equal to a ratio. And tangent of an angle is equal to a ratio. Let's spell this out. I think we just did there. Man, I really want to write it again, though. So we have sine of an angle is equal to a ratio. And just while I'm writing this, what is the ratio? This is opposite over hypotenuse. Sweet. Cosine of the angle is a ratio. It's the adjacent over the hypotenuse, but it's still a ratio. Tangent of an angle. If you don't have this down pat, you know what I mean? Like I said, go back to, hey, this is sine over cosine. Oh yeah, sun is shining on the sine, that's the opposite over the hypotenuse. Still a ratio though, but tangent is this over that. Okay, hell yeah. Now, why I did this is because the point I'm trying to make is that if you change the ratio, you change the angle. You know what I mean? No matter what you have. If you change the ratio of tangent, the angle must change. You know what I mean? And you know, because when I misspoke, I was just like, hey, you could have a triangle that's this small, and then just increase it to a triangle that's this a little bit larger, and maybe these angles, angle 1, angle 2, maybe they're the same. But guess what? The ratios, all three of these ratios are the same. The sine of the angle is the same ratio on both of these. Because the angle is the same, you're going to generate the same ratios. So changing the ratio will change the angle. All right, hell yeah. And cool. And this is important when it comes to derivatives, because when we start writing the derivatives, hell yeah, we're going to change the ratio, and then we're going to change the angle. And then it asks us, hey, we want to find the change in the angle. We want to find the angular velocity. That's change in the angle. You know, every second we want to know what the angle is going to change. That's literally the definition of angular velocity. And let's talk about angular velocity real fast. We have a circle. Hey, this is the radius, and this radius is going to sweep out. Always refer to what a radian is. A radian is when you take the radius, maybe measure it with a string, and then drape it around the circle. That radius would get to about there. That's going to be the definition of 1 radian. It is an angle, so you can say theta is 1 radian. Cool. It's approximately 60 degrees, so you could say theta is approximately, 60, or it's 57.3. Hell yeah. And anyway, cool. Where are we at? Oh yeah, and then so angular speed. So this is going to be in degrees. Angular speed says, hey, let's say I'm going around this circle and it takes me 1 second to do that. Just know that there's going to be about 6 of these, but there's just a little bit more. It's a 6.28 of these. So you got 6.28 radians in a circle. So I'm just going to say my angular speed, we use that as omega. I'm just going to say 1 radian per second. And so it takes 1 second to get up to there. So we got 0, 1, 2, 3, 4, 5, 6. And sorry I drew in this, but take a circle, divvy it up into 6 chunks. Those are all 60 degrees, which is about a radian, but just a little bit less. So you're always just be kind of just a little bit less until you got to add 0.28 radians. All right, hell yeah. So that's angular speed, the angle per second. All right, sweet. So I think let's just dive into this derivative. All right, so what I'm going to do, I'm just going to call this h, and I'm going to call this x. And what we're going to do is just set up an equation that just relates these 3 things. And, and you... Oops. Alright, hell yeah. That is absolutely not what we're going to do. What we're going to do is we're just going to get an answer to the problem. Because the issue with derivatives is there's just so many places to make tiny little errors. And even on the setup. So what we're going to do is... so I use the 3-point method. And for velocity, you only need 2 points. We're just going to say the angle's 30. Cool. So we have 30-degree angle. Now... this thing is going to move at 1.2. It's got a velocity of 1.2 feet per second. This is only, what did we say, the square root of 3 times 2. This is only 3.464. I'm just going to write it to 3 decimal places. So that's what this distance is right now. Let's say in a 1 second, it's going to be minus 1.2. You know what I mean? So that's the other thing with problems. It's just like, oh, I could see that. If this is 3.5, maybe in a second it's to here, and then I would have a bigger angle. You know what I mean? So that's kind of what we're shooting for. So you could do that. I don't want to, but let's do it. I want to use 1/10 of a second just because that's going to be like the most dialed in. It's not too sloppy, but you're going to get closer to the answer. But since we just did this, alright, so we're just going to subtract 1.2. And you can do this in your head. That's going to be 2.264 feet. So now we have a triangle that's 2.4. So, and then we're just going to get back this. So we have 2.264, 2 feet. And you can kind of see what the angle of that is. Maybe it's close to 45. Maybe it's close to 40. We can find this angle just knowing these two sides. So at least we know that much. We don't have to involve the hypotenuse. You could say, hey, we're going to square this plus the square root of that. So we're going to square this plus 2 squared, and then take the square root of that. Now we have the hypotenuse. So now we could say sine of the angle is equal to 2 over the hypotenuse. And we could do inverse sine of 2 over the hypotenuse, and that would give us the angle. I guess we should go back to here, because if we take the inverse sine, what do we take the inverse sine of? The ratio. If we know the ratio, in our calculator we type the inverse sine button, and it's not the 1 over ratio. We don't take, if the ratio is 1/2, it's not 1/2 to the 1. It's not, the number doesn't become 2. It's like, hey, if we have a ratio dealing with sine, and so this spells it out. You know, you do your triangle. If here's my angle, I know the ratio of sine is opposite over hypotenuse. So it's going to be this, in our problem it's going to be 2 over 4. And just a unit, if this is 1, this is going to be 0.5. You know what I mean? So you're going to get this, you're going to get that ratio, 0.5 over 1. That's going to be 1/2. But it's this ratio, whatever triangle this ratio is, that's the angle that's going to pop out of the calculator. So I guess I didn't spell it out enough. It's just like, hey, if you know your ratio of like, hey, I know, and we can just do it. We could do some. I mean, what should we do a ratio of? Well, and the only thing is that the ratio of sine and cosine have to be between 0 and 1. The ratio for tangent can be negative infinity to infinity, but let's talk about that, because I would say it's negative 60 to 60, or it's negative 57 to 57. If you can remember that 57, because this is going to be the ratio if you have a tangent of 1 degree. But what would be a tangent of 4? Tangent of 4 says that this opposite is 4 times the adjacent. So there we go. 1, 2, 1, 2, 3, 4, and then the adjacent is just going to be one of these. So that angle right there is a tangent of that angle is 4. So if I go inverse tangent of 4, I'm generating this angle. So I could, if I put in my calculator, and are we in degrees? Hell yeah. If I put in my calculator inverse tangent of 4, hey, I should be able to get like 72, 74, I don't know, let's try it out. Inverse tangent of 4, 75. So sweet. So just improving your trigonometry guessing skills is really important. And then, like, why did I say 50? Because inverse tangent of 57 is just 89, you know what I mean? And how it goes to infinity, but where are you in the real world going to be making like tables that, I mean, just anything with precision, you're not going to, there's going to be no difference between 89 degrees and 90, or, I mean, that makes no sense, but I just don't think, it comes in, like the one thing, like a slack line. Sure, if this slack line is so tight that when a person hops on it, it doesn't generate any angle right here, hell yeah, you can generate an infinite amount of tension. But we just know that's not possible. That this will slack because it has to have a component, a tiny upward component of the vector, a huge component this way, that's the tension, to hold up. This tiny component has to equal half that person's weight. The other one will equal the other half. But But yeah, to say that angle is going to be less than 1 degree, so that's where I'm bringing this up. There's a lot of problems where you're not going to get an angle less than 1 or in between that 89 to 90. So hell yeah. So let's do it. Inverse tangent, 57. Let's do 57.3. And booyah, you get 89. So that was the reason why I wanted to go over that. All right, sweet. And then, so let's do a cosine one. I want the ratio to be, 0.25 for the cosine. I really don't. I want the ratio to be, how about 0.7, like 70%. Could I do that? I'm going to do this. So this cosine, what does the cosine say? The cosine says this adjacent part is going to be 0.7, and this part's going to be 0.1. So let's try to draw that. I don't have any extra sheet of paper. Let me fold this. Yeah, this will be a good one. But what's the ratio of cosine? It's going to be this hypotenuse to this adjacent. That's it. So we're going to go 1, 2, 3, 4, 5, 6, 7. And then we're going to have, but the only stipulation is you have to have a 90-degree angle. So maybe I should grab even another sheet of paper and do this. So I'm gonna, and this is real smart. Like the statics book, especially in the first few chapters, they say, heck yeah, you should be doing this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're calling this 0.7, or there's 7 units, and this is 1, or there's 10 units. And so this has to line up with there. So there is going to be, so that's a 1, this is 7, and there you go. So, and check this out. What does this turn out to be? It turns out to be 1, 2, 3, 4, 5, 6, 7. Just a little bit more, 7.5. But pretty close. If this was 0.707, this would be 0.707. And I'm sure I just have a little bit of error. But this is your 45-degree triangle. All right, booyah. All right, that was a good little aside. And hell yeah. So we just, so we got back to here. So same thing with inverse tangent. So we have, we're going to do inverse tangent. Because now you can just go for it, Or, don't. I would start with the basics. Always know your sine of your angle, your cosine of your angle. Those are percentages of the hypotenuse. And your tangent is going to be sine theta, cosine theta. Like those 3 things are about all you need to know, and then just know the Pythagorean's theorem, and then know how maybe Pythagorean's theorems, sine squared plus cosine squared equals 1. That's useful. But hell yeah. So you can be like, oh, I just know both the sides. I know nothing about the hypotenuse. That spells tangent. So I'm going to write tangent of this angle is going to be 2 divided by this distance. Oh, sorry, we already know it. So what we did was we took this length, we had this velocity come in, and we shortened it to that. So this is the triangle. So it's 2 divided by 2.264. Okay, so if this is the equation, to get the angle, we say the angle is the inverse tangent. And I guess you can write it like this. You can do inverse tangent, and it's not an exponent. So inverse tangent of this, inverse tangent of both sides, inverse tangent of the tangent. And does that make sense? Because if we come back here, I guess I should probably write them again. So we're going to say sine of the angle is the ratio, opposite over hypotenuse. Cosine of the angle is the ratio, adjacent over hypotenuse. But writing like this, it really hammers home what these are. Whoops, tangent, damn it. Alright, tangent of the angle. And then we're going to write inverse sine. So inverse sine, now what do we put in here? Inverse sine of the ratio is the angle. Inverse sine of inverse cosine of the ratio is an angle. And the one we're working on is inverse tangent of the ratio is the angle. So we have an inverse tangent of 2 divided by 2.264. So even before putting this into our calculator, we can be like just 1, 2, the opposite's 2, and then the adjacent is 2.5. There's our triangle. Sweet. You know, just guess. You know what I mean? Hey, this would be 45, this would be 60. Looks like about 30. Cool. Maybe it's just 35. So now we'll go to our calculator. Inverse tangent of 2 divided by 2.264. And we get an angle of 41.457. I'm going to store this in my calculator as alpha C, and I'll show you why in a moment. If our original angle was 30, I'm going to store that as alpha B. Okay, so now we can actually solve the problem. We can find the angular. We have enough information to solve the problem, because we know that we went from an angle of 30 to an angle of 41, and how long did that take? We said we went for 1 second. So we did a change in time of 1 second. So I think that's very, visual. I think it's very easy to do that. And so we went from alpha C. So we're going to minus 30. So we went 11.45 degrees in 1 second. So if you write it like that, hell yeah, it's just like a velocity problem. You're like, oh, sweet, I went, 60 miles in 1 hour. Cool, you went 60 miles an hour. So we went 11.45 degrees in 1 second. Okay, we're going 11.5 degrees a second. Sweet. None of these problems will ever be in degrees. So you can always switch. It's good practice to start using radians. So if if I have a circle and this is the radius, drape it out to there. Heck yeah, I get to 60. That's 1 radian. So cool, if 60 degrees is 1 radian, 30 degrees is going to be 0.5 radians. 15 degrees is going to be 0.25 radians. And so on. All right, to convert to radians, so we have this radius. Let's say it's 1 meter. This is the really bizarre thing about radians. They're very useful, but maybe it's just by design. No, it is useful, because if you used angles and diameters, which would be over here, you would not have the small angle theorem. The small angle theorem says, basically, if I have 1 meter and I go up to 1 radius, even at 60 degrees, it's saying that this height right there is the same as that arc length. And obviously, this is at 60, that's going to be bigger, but at an angle of 30, you know what I mean? Here's your, if here's your circle and here's 30, this height, yeah, these are about the same. And that's kind of what that small angle deal means. That's it. It just says, but then also it says that if I know this angle to be 0.5 radians, and I take radians times my radius, this gives me my arc length. So if my radius is 1 meter, and I got 0.5 radians, my arc length is 0.5 meters. You know what I mean? So that's what we have right there. If we had diameter, I really want to do this one because it's kind of fascinating. I haven't done it in a while. But if we had angles and diameters, where, hey, this is a diameter, we started draping this around a circle, you'd get to a third. So you'd have to chop this thing up into that third. There would be 1, 2, and then 3. But you'd have 3.14 diameters. Okay, so that would be one diameter, and that's going to be 180 degrees. So then a half a diameter, 1/2 diameter is 60 degrees. And then so 0.25 diameters is 30 degrees. But if we have a 30 degree, if we have a circle and we swipe out 30 degrees and we call this 0.25 diameters, but the actual radius is 1 meter, this height doesn't magically become 0.25 meters. It's still 0.5 meters. So that, I'm so glad I said that, because, I mean, that's why I think my videos are pretty decent, because I'm going to go over stuff like that. I just pretend that I was in college, and then I could, like, talk to myself. Like, I'm kind of like, feel like I'm, like, time traveling back to when I was in college. Is if someone explained that to me, I would have been real happy. Like, why the hell radians? And why they're kind of magically nice with this small angle thing, where the actual, this being 0.5 in radians, can be this height. Can be this, well, one, it can be this height for hella sure, and also it can be that arc length. Like, it's kind of like it's a trifecta. This angle is equal to the sine component, is also equal to the arc length. Alright, hell yeah. But if you had diameters, you would be off by a factor of 2. You know what I mean? So there you go. So that covers that. Alright, sweet. So now it's honestly one of the harder things, I swear, to do, is converting degrees to radians. And I would just do it as much as possible. The way I would do it is spell out at least DEG divided by S, and then use factor label. You know what I mean? Hey, if I have to convert, like, what do I know about a circle? Like, hardly anything in radians. I know that 1 radian is 60 degrees. I mean, you could do that. That's kind of a cool. I could be like, hey, 1 radian is 60 degrees. It's not, though. Like, 1 radian is 57 degrees, and that gets you closer. 1 radian is 57.3 degrees. But if you did that, you would be like, hey, 57.3 degrees is 1 radian. Okay, sweet. And I just converted to radians. So I take this, I'm going to store that as x. We're going to do this a couple times. Divided by 57.3. Booyah. That's going to be 0.2 radians. Now, the way to do it 100%, so you have 11.5 degrees, is we say that, well, let's go, I mean, I don't know. There's 2 pi radians in a circle. No one knows what the hell that means. I think it gets lost. But if I said we measured angles in diameters, yeah, I'm so glad I brought this diameter thing. Well, what's the circumference of this whole thing? It's pi d. Like, pi d has been in our head since elementary school. The fact that a circle has a circumference of 2 pi times the radius is just a little bit like one step like less, but the fact that a radian, like the degrees in radians times the radius is the arc length. That means that 2 pi radians times the radius of 1 meter is the circumference. But you still have to take, radians still are dimensionless. So you have 2 pi dimensionless units, but if you multiplied them by that radius, that does give you the circumference. So it's still one of the hardest factor label methods. Like, I for sure graduated without, not really wanting to fully understand how to convert degrees to radians. But you can do it this way. One circle is 360 degrees, and you get 2 pi radians. And you can even spell it out. I would spell it out like 4 different ways. 6.28 radians divided by 360 degrees. Do this for a long time before you get good at just doing 1.5 degrees per second. And then, you just do, because obviously if you just half this ratio, you're going to have 180 degrees divided by pi radians. And that's just easier to put in your calculator. If I know that I'm in degrees, what I like to do is just divide by 180 and then go second pi. And this does not put the pi downstairs. It's the same thing as doing this 11 times pi divided by 180. That gives you the same numbers. Okay, so that's the angle, and that's going to be my angle in radians. Holy Toledo, I forgot even why the hell we just did that, because, cool, now we know our speed. So we have our omega, this is going to be angular speed, and this might be the only way you know how to write it. Angular speed is going to be 0.2 radians per second. Alright, hell yeah. Now, we haven't even touched differentiation, but I would never start a differential problem without doing this method. So now, the angular speed isn't 2 radians, so we need to up our game. So what we're going to do is we're going to go back and, we're actually going to go, this thing's traveling this way at 1.2 feet per second. Now we're going to do 1/10 of a second, but we're going to start going that way. So what's this length? Square root of 3 times 2. So this length right here is 3.464. We're still going to be working in decimals. If I go this direction, this length increases. And if we have a change in time of 1/10 of a second, hey, we're traveling 1.2 feet in 1 second. See, this is the stuff you can do mentally. I'm going to travel 0.12 feet in 1/10 of a second. Sweet. So if I take the thing backwards, I'm going to be adding, so it's going to be 3 point, and we're adding 0.12, so it's going to be 3.584. And then this would still be 2. That would be the ratio of that triangle. And then we have this triangle at 2. So this is going to be t equals 0 seconds. This is going to be t equals -1 second. And then we're going to go forward. If I go forward on this, I'm going to subtract 1.2. So we're going to have 3.344. And then 2 for that side of the triangle. And so, hey, we have these ratios. I'm so glad we talked this over so much. So sweet. You can totally see that we have a tangent of all these. It's going to be the ratio, between this and that, and each of these tangents is going to generate an angle. And we spell that out just by going just to the inverse tangent. So whenever you're watching like fancy lectures of professors that don't slow down, they'll just go right to inverse tangent. Inverse tangent still means that ratio of 2 divided by 3.344. And again, when this gets smaller, this stays the same. Hey, your angle gets bigger. Cool. So this is going to be our bigger number. In our calculator, I'm going to store this as C. This is going to be 30 degrees. I'm going to store that as B. And then this is going to be A. And you can kind of see how we're going to get, we can get 2 numbers for velocity. We can find the velocity from here to here, and then we can find the velocity prior, and we're going to have a change in velocity because we also want to know the angular acceleration. Because this problem won't have the same change in angle, and to spell that out is you kind of make, you say, hey, this is 2 feet, make this ladder really long, and then say, hey, I'm going to slowly move this way. You know what I mean? Well, did my angle, let's say like, hey, did my angle change just by moving it? This angle is pretty close to that angle, but at some point, like not changing, but at some point, like, hey, look at these 2 distances. Let's compare them to this distance, these 2 distances. So we're going to say, hey, this angle compared to that angle. This angle compared to that angle. Now we're really increasing. So, like, there's going to be so we took this problem to the extreme. You can move this, we hardly change the angle at all. And at some point, hey, the angle is changing more and more. And so, for this problem, the angle is always going to be changing more and more up until you get to the stopping point. Alright, hell yeah. so we're going to go inverse tangent of 2 divided by 3.344. So this is going to be 30.8. 30.9 degrees. I'm going to store that as alpha c. We have the exact answer in our calculator. Alpha b is 30. Inverse tangent of this one, 2 divided by 3.584. Whoop. Inverse tangent 2 divided by 3.584. And we get 29. So we're going to store that as alpha a. Now to get the angular speed, so let's say omega is radians per second. This is also the change in the angle, change in time. Write it like this first before you ever write d theta dt. I write it like this for years upon years before ever being like, no, I kind of grasp this, you know, I mean, even though this is supposed to be an infinitesimal change, you don't have to think of it like that. You could be like, well, it could still be a visual amount of change, but if you do a visual amount of change like this, you're going to get close to the right answer. Hey, you're approximately, but not quite. Cool. But the other way, there's a few other ways to write this. This is also, you know, theta dot. This dot just means, hey, d theta dt. That is special for theta dot. And the reason you would do this is because it just makes your problem sets cleaner, and you just have to way less pen strokes. All right, hell yeah. So in our calculator, alpha c minus alpha b is that change in our angle. And this is still in degrees. So we have this change in angle, and it's going to be a change. So our change in angle is 0.89 degrees. Cool. Our change in time, we said, was 0.1 seconds. Sweet. So that's going to be 8.9 degrees. And we're going to take that 8.9 degrees. We're going to say 180 degrees is pi radians. Cool. And that's going to change to radians. So cool. We're going to take this divided by that change in time. And we could just, hey, the degrees. Hey, I'm going to divide this by 360. That makes more sense to a lot of people. I have a full circle. This is 30, so I have about 10 degrees. I'm going to say, hey, this is 8 degrees divided by 360 is, well, it's you know, it's 2.4% of a circle. It's 0.024 as a fraction. You know, it's that much as a fraction. So it's 1/40th of a circle if I invert that number. Invert it again. But then if I take this, what's 1/40th of 2 pi radians? You know, that's basically what we're doing. So we're going to multiply this by 2 pi, and we get 0.154. And so, I'm sorry on my units. We already got it, degrees per second. So this is angular speed in degrees per second. Once we convert it, we get 0.154 radians per second. So now what I'm going to do is how I solve these problems just with calculator. I already know kind of how to do the easy approach, because the easy approach is very intuitive. I'm going to say, hey, my initial angle B is 30. And I'm going to set my change in time. I'm going to do 1 divided by 1,000, 1,000th of a second, 0.001. I'm going to store that as alpha t. So now this velocity is 1.2. So I'm going to say 1.2 alpha t is this distance. Prior to this t equals 0, this initial time, this thing was 10 thousandths of a foot that way. Okay, but okay, cool. So we're going to take this square root of 3 times 2 minus that answer. And how did we do that? So we took square root of 3 times 2 minus 1.2 times that time. And keep track of what we did right there. I always kind of work backwards, but we'll do that later. Okay? So we have that distance. I'm going to say inverse tangent 2 divided by that. That's going to be my angle prior, alpha A. Alpha B is 30. And then we're going to take that square root of 3 square root of 3 times 2, and now we're going to add that 1.2 times a thousandth of a second. Inverse tangent 2 divided by that rate. So we have inverse tangent is... Alright, hell yeah, my camera cut out. So we're doing the inverse tangent of that second angle, and we're going to store that as alpha c. Okay, and I totally forgot, back here I only got the speed. I mean, we put in 3 values into our calculator. Maybe we didn't, but we got the velocity. So here we'll be able to get, I'll show you in a second. So we have those three angles, before, 30, and then after. And so we're going to go alpha c minus alpha b. So that's going to be the change in the angle. Oh, do I have these written wrong? Yep, my bad. Sorry about that. Alpha A should be alpha C. I'm going to store as alpha F. So that should be stored as alpha A. Yep, and then alpha D, the bigger one, stored as alpha C. Okay, so we have alpha A, alpha B, alpha C. Just get them in order. Beforehand, this angle was shallower, then 30, and then just a little bit steeper, more angle. So we're going to have alpha C minus alpha B. That's going to be the change. We're going to increase our angle, and we did that divided by alpha T. So we have that change in angle divided by that change in time. So we have a change in angle of 0.008. 5 divided by 0.001. Cool, you can see that's going to be 8.5, 8.6 in this case. So that's my velocity. I'm going to store that as alpha E, and then we're going to do the same thing. Alpha B minus alpha A divided by alpha T. I can even store that as alpha D right away. So perfect. So we have that velocity. We need to change them to radians, so I'm going to bring that up, that first velocity. We're going to divide by 180 pi. Multiply by pi, divide by 180. I'm going to store that as alpha j. Alpha d, divide by 180, multiply by... Multiply by pi. Whoops. And we're going to store that as alpha I. So our speed going in is 0.149. Our speed going out is 0.150. So now we have these two velocities. We have this velocity at t is equal to minus 0.001 seconds, and that's going to be 0.14996, and then we have v at plus 0.001 seconds, and that's going to be 0.1500. And these two are not 0.002 seconds apart because they're averaged. You know, it's actually, this velocity is halfway between t is equal to 0 and t is equal to negative 0.001 seconds. Or I kind of said that wrong, but this one is halfway between 0 and t is equal to positive 0.001 seconds. And because it's the average, it's the velocity right in the midpoint, when we take these two velocities and find the change in the velocity, change in time, that change in time doesn't change. It's still 0.001. I think that's the only thing that might get confusing when doing this method. You're just like, well, I took the velocity from here to there in a small fraction of a second, and I took the velocity from prior to that to there, that same time frame. But you can consider that velocity halfway, and then and between these averaged velocities, that time frame is the same time frame, that a thousandth of a second. Okay, so without further ado, let's find that. So we're going to have alpha j, which is our velocity. It's speeding up. I mean, the angles is speeding up. And does that make sense? Because if we're out here, hey, the angle's, the angle's about 5 degrees, 5.1 degrees. It's hardly changing. But then here, maybe it goes 5.3. So we have an increase. So the acceleration of the angle, the value of the angle is increasing. So that's going to be angular acceleration. And let's do our circle. If I have a speed of 1 radian per second, so I'm going to go from here to there, to there, to there, to there. It's going to take 6 seconds, to get around a circle. But so that's going to be my speed, 1 radian per second. Let's say my angular acceleration is also 1 radian per second. So, oh, we're going to start at 0 radians. So this is going to be confusing, but it's going to take 2 seconds to get to 1 radian. Because we're gonna have a speed of 1 radian per second here, 0 radians per second here. That's gonna be an average speed of a half. So over this is gonna be like 0, 1, we got halfway, 0, 2, we got that far. But between here and here, we're gonna increase to 2 radians per second. Average speed of 1.5 radians per second. So we can actually do this in 2/3 of a second. You know what I mean? So it will be 0, 1, 2, and then 2/3 of. So it'll be 0. So 0 time here, 1 second, 2 seconds, and then we'll be to here in 3 seconds. So, and obviously it's continuously increasing, but that kind of gives you the idea of the difference between angular speed and, hey, if something's increasing. And man, I just touched on it briefly. But if you go back to kinematics, it's the same thing as something, an object. You jump off and you're doing some cliff diving and jumping. In 1 second, you're going to go 10 meters per second. You know what I mean? You're going to be going 22 miles an hour. But here you're going 0 meters per second. So what's your average speed? Your average speed is 5 meters per second, and it took you, like, this was at 0 seconds, and at 1 second we clock your speed at 10 meters per second. So, but your average speed is 5 meters per second for 1 second. You traveled 5 meters. So that's how that worked. Same thing for radians. I'll make more videos on that, but we're just really just glossing over that. So anyway, so we have these two velocities, alpha j minus alpha I. That's going to be our change in velocity. That change in velocity is very small. And then so divide by alpha t. And so, but you know, I mean, it's something. So we have a change in velocity. Well, a change in angular velocity is angular acceleration. That's the definition. Definitionally, angular acceleration is a change in angular velocity, change in time. That's going to be a change in omega. Yeah, we already said it. So omega is a change. So it's a change in the change of the angle divided by a change in time. Oh man. Oh shoot, I don't have enough paper for that. But yeah, I kind of. But anyway, so so there you go. So that's going to be 0.779 radians per second squared. But anyway, the reason we did that, and let me grab just kind of a sheet of paper, is so that we can. It's so that we can get some values on this. You know, so right now, we know. Okay, and then we can actually find the average. So D and E, or I and J were the average, was the velocity before and the velocity after. So we can actually average those. The equation for that is just adding them together, dividing by 2. So sweet. So we have angular speed is going to be 0.15. I think that's 100% accurate right there. And then angular acceleration is going to be 0.07, what was it? Yeah, 0.0779 radians per second squared. Sweet. Okay, so those are the two values, and now we can start in on differentiation. The reason we do it that way is because when we do differentiation, we might make hella mistakes. I even got to print off more sheets of paper. Alright, hell yeah. So we're ready to start in on differentiation. And what we're going to do is just label this x. And then we're just going to label this h. Alright, and then we're just going to make a relationship between these two things. We don't have to involve the hypotenuse, you know what I mean, because it's not specified. This is the length that's changing. So we're just going to go tangent theta is equal to h divided by x. Okay, heck yeah. And And, you know, if you get a relationship, you can just start you can just start differentiating. And so what we can do is just differentiate with respect to time on this side and differentiate with respect to time on that side. And that, I don't know, it might seem kind of like, well, why the hell did you even do that? And you might strike out because you might not have related the things that you related. But anyway, that's why I'm just trying to learn differentiation from the standpoint of like, hey, is there a way just to not mess up? You know, can you get a relationship and say, hey, we're going to now change things, you know, differentiate with respect to time, and just have things kind of make sense. Now, the most important thing about differentiating, especially when with respect to time, is that, hey, we don't have, this says theta. That doesn't say, you know what I mean? And then, you know, sure, this theta is changing, but maybe theta is a function of time, and then we'd actually have to write something in with that. Could we figure out what x is as a function of time? If we have x as a function of time, our position is going to be, hey, it's going to be like 3.46, but it's going to go minus, it's going to be minus, and then that velocity, that 1.2, and then times time. So sometimes this can be spelled out because how did we initially started with square root of 3 times 2. So we initially started out with this distance of 3.46. And then let's do what we did in 1/10 of a second. We came in 1/10 of a second. Our velocity is 1.2 feet per second. And so we said that this distance decreased. So it's going to be minus 0.12. And then so we get 3.34. So that's going to be, and then whatever we did there should be the equation for x as a function of time. Cool. But the cool thing about the way they answer this question is that we don't have to even bother with that. Okay, but we do need to know the chain rule, because I can't differentiate this with respect to time because I don't have anything that says time there. What I need to do is say, hey, we need to say this is differentiating with respect to theta is tangent theta. But then I do need to say this, d theta dt. So this is the classic, like the chain rule says, sure, you can I mean, basically you want to know, and we could figure this out. I mean, you could say, hey, the tangent at 30 is going to be 2 divided by 3.46. Okay, yeah, because I did a video of just like, what is the differentiation of tangent? Mainly this one. What's the differentiation of tangent just with respect to that angle? And how do you even say this? Well, so let's do this one first. So the tangent at 30 is going to be well, it's going to be this ratio. Hey, this is going to be the angle because we've already said that. So we have tangent of this angle, 30, is going to be the ratio of this to that. That's going to be 2 divided by 3.46. Sweet. But then when we increase this in, like after a second, this 3.46 subtracts by 1.2, we get this 3.42. So the ratio here is going to be 2 divided by 3.34. So we have 2 divided by 3.34, and we get a ratio of 0.499, and then this ratio is 0.578. So we're going to have a change in that ratio from 0.599 minus 0.578, so that ratio changes by 0.021. And how much did the angle change? Well, I'm going to say the angle is going to be inverse tangent of 2 divided by 3.34 I'm going to store that as alpha h just for now. And then the other angle is going to be 30. So we're going to have alpha h minus 30. Whoa. And so that's how much the angle changed. So the angle changed by 0.91 degrees divided by 0.021. So I'm going to store that as x just for now. So we're going to have that x divided by 0.021. And we get a number. You know, it might not mean anything, but we get a number of 43.48. Holy Toledo. No, I did it in the opposite. I did it in reverse. So we found the tangent of the angle was the difference between those two, and that was going to be, the tangent of the angle is going to be 0.021. The actual angle changed by 0.913. So we got 0.021 divided by that x, and then heck yeah. So this is the so the derivative of that is going to be 0.023. But this number is probably nonsensical because it's the change in the ratio of the tangent, right? But divided by the change in degrees. So we would actually need to change this. We would multiply by 180 degrees divided by pi radians. Let's do that. So multiply by 180 divided by alpha pi, and we're going to get inverse tangent of 1.317. And the more that you actually put in, and this is the differentiation with respect to theta of inverse tangent of 30 is approximately 1.317. And so that's, I guess if you're not understanding what differentiation is, just always change the top and then change the bottom of what it is. But in this case, we didn't change it by time, we changed it by theta. Now we could change it by time, because how many, what did we do for our problem? That was going to be 0.1 seconds. So we're going to have 0.021 divided by 0.1, and that's going to be 0.21. 0.21, we're going to have a change in that ratio of 0.21 divided by change in 1 second. Because it's 0.021 divided by a tenth of a second, that's going to be 0.21. That ratio is going to change every second by about 0.21. And, yeah, so there you go. And that's the first thing we did. We said, hey, in a tenth of a second, this is going to decrease. Square root of 3 times 2. It's going to decrease by 0.12. And then so, yep, but this 2 will stay the same. So we're going to have 2 divided by this. That's going to be the ratio minus 2 divided by, oh, I feel like I'm doing this wrong. Nope, no, this is the bigger, the first one's the bigger number, so hell yeah. So that ratio is, that's the other thing, the derivative of tangent always increases as the angle increases. But yeah, if you're doing differentiation, like this might be the last thing you do of just like trying to figure out, because it's still kind of meaningless. Cool, what does it mean that the tangent changed divided by the change in time? Well, it just, I mean, this actually is a identity. It's like, hey, if you change h, which h doesn't change, but then you change x, cool. That is the, that's going to be the change in the tangent. Yeah, if you change x with respect to time, you know what I mean? Because, yeah. So that's basically what we just did. We said, hey, let's change it by a tenth of a second. This x will change, and then so we're going to have a new ratio. That h divided by x is going to be a new number. This x is going to get smaller So then this ratio gets bigger, and we're going to subtract that from 2 divided by when x was a little bit bigger. So this is going to be a positive number, and yeah, sweet. Alright, hell yeah. So at least we got that far. So we're going to do the derivative. Well, I guess first we're just going to have this. This is going to be h, this is going to be x. Tangent of the angle, h divided by x. Cool. So now we can just differentiate with respect to time. And again, we do this chain rule. So we're going to have... and the other thing with differentiation, I would do this d and then put in parentheses and say this is what I'm changing. I'm going to change, and then what is this? This is the angle, but taking the tangent of it, this is the ratio. So I'm going to change the ratio with respect to the change in the angle. And then chain rule says that I have to take the change in the angle dt. So see how these can cancel, and you're going to be back to that. And so I think the hardest thing learning differentiation was that these letters actually mean stuff. You know what I mean? It is like this d does mean you're changing this. You know, that's why you can say, hey, a change in tangent of the angle divided by a change in time. Sometimes this just looks more familiar. And so obviously then the change in the tangent of the angle divided by a change in the angle times the change in the angle divided by the change in time. Like obviously this, you can easily see that these cancel. So just, I mean, this symbol kind of puts more numbers on it because we're taking bigger chunks. But even you could take really tiny chunks just like we did down to 1,000th of a second, and you know, you still get you get the exact answer as the derivative basically. Cool. Alright, hell yeah. So this is this side. Let's do it to the other side. So again, we're going to have tangent of the angle is equal to h divided by x. Now here's the other thing that's going to be very useful. Anytime that you have a quotient, let's try to get everything just upstairs as a product. Cool, so let's do that. So we're going to have tangent theta is equal to x to the x minus 1. Now the other thing here is let's treat everything like it could be changing. I think one of the worst things that I think gets taught in differentiation, now actually kind of learning it, is treating constants like, oh, just like a hand waving. You know what I mean? Hey, if I do, and maybe we'll get back to that. Maybe we will just say h isn't changing, and so you can just hand wave it outside of the differentiation. But no, this will be the first thing that we go over. So we're going to take the derivative of both sides with respect to time. So we have to use the chain rule. So this becomes d tangent theta, d theta, but then d theta dt. And then you just need to know that d theta dt is omega or theta dot. You know what I mean? These three are just synonymous symbols. So then you can just easily write theta dot. That's what I would get used to, as a pro. But you can also just write omega too. That'll take care of it. But theta dot will just be, you'll have more understanding of how things are changing. Okay. And then let's set this up like it is the product rule. For differentiation, we got a product of two things. We're going to take the first times the differentiation of the second. So that's going to be h. But now check it out. So let's just keep writing it. d dt of x to the negative 1. Hey, this says x right here. It doesn't say t. This says t right here. It doesn't say x. Okay, but let's continue on. So the first times the derivative of the second plus the second, and I'm just going to reverse the order. So I'm going to go x to the negative second, and now we're going to take the derivative with respect to time of h. But cool. So again, I don't see a t here. And I don't see an h here, you know, or I see a t here, I don't see a t there. Okay, so let's hold off on this derivative of tangent with respect to theta, but now we can do that one since we have the chain rule. I'm just going to go right to theta dot. Let's get used to that. Sweet. These are two different things, and the other thing is, hey, this is still in parentheses. This derivative only tackles the parentheses, not what outside. You're not taking the derivative of tangent theta and this d theta, you know, so don't get that confused. Hell yeah. Alright, so we're going to do the chain rule here. So we're going to have this h. Well, h is just a variable, you know what I mean? It could be changing, it could not be changing. But we have h, and we have, so to make this the chain rule, we're going to take d dx, because that's what we have here. Just like we had theta here, we had to say d theta. We need to change this we need to change this ratio, and then divide it by a change in the angle. Cool. And then over here, we're going to have change in the angle divided by change in time. And that's kind of the magic of these things, because this is what we're trying to shoot for. So once we do all the differentiation, we'll try to get this by itself, and then we'll have an equation for the angular velocity. This is angular velocity. Hell yeah. Okay, so we're doing the chain rule here. D dx, and then we have that x to the negative 1. Put it in parentheses just so, hey, you know that you're taking the derivative of this. And what I mean by that is like, hey, we know how to take the derivative of x squared. Dx is going to be 2x. You know, we kind of know those power rule properties for that. For the tangent ones, you might have to look it up in a book, but we'll actually be able to do this one pretty straightforward. Cool. All right, so, and then because it's the chain rule, it's it should be d dt. We just changed it to d dx, so you can only do that if you do dx dt. And cool. Now, what is dx dt? Well, that's velocity, or that's x dot. You know what I mean? So that's, you know, just like change in velocity, change in time would be acceleration, or v dot, or x double dot. Sweet, and we'll talk about that in a second, or later too. Okay, hell yeah. So that was just that term right there. We're going to add it to this x to the negative 1. Now we're going to have to do the same thing, but this one's going to get a little bit maybe bizarre, but we're still going to do derivative with respect to h of h. Sometimes I'd like to put the power on. This is h to the 1, and then you're going to have dh dt. Or dh dt is h dot. All right, so hell yeah, let's really simplify this. We're going to have d theta tangent theta dot is equal to h. We can do this one. It's going to be negative 1 x to the negative 2. So we did the differentiation on that, and this is going to be x dot. X dot is just velocity. Sweet. And then plus, we have x to the negative 1. We have to differentiate this. This is going to be, bring down the 1, and then it's going to be h to the 0. Cool. And then, but this is going to be h dot. So this is, and then we know that h isn't changing. So we know that h dot, this is just something just from observation, just from how the problem is set up. You can go back and be like, oh, h dot's not changing, so that's 0. And you could have done that right back at the differentiation process, but let's simplify that and go back and show you that. I'm still going to keep this the same. This, I'm going to say negative h divided by x squared, and then we have an x dot up top, plus, this is h to the 0 is just 1, and then so this, but this h dot is, this whole term is just 0, so we're done here. And just by a book definition, derivative of tangent theta is 1 over cosine squared theta. We will do that, but then you're going to have theta dot. So sweet. So this is your differential equation. And what we're looking for is this angular speed. So let's just get this up top, and you're going to have theta dot is equal to negative h x dot divided by x squared cosine squared theta. Now, this is how I initially did it, and then I realized, oh, in the book, this isn't what they wanted, because we have angular speed theta dot as a function of hey, we have a function of theta, but this is also a function of x. So how to get this as a function of just theta is, well, let's go back to our equation. So we're going to say tangent of theta is h over x. Okay, so let's solve for x. So x is equal to h divided by tangent theta. And then we're going to have to cancel some things. So what's tangent theta? We said tangent theta was sine theta divided by cosine theta. So sweet. So that's what we have. We have x is equal to h cosine theta divided by sine theta. If we put this in for this x term, then we will have a function that's just a function of the angle. But it will be a function of velocity. This x dot is that velocity term, but that's just this velocity that's given. This velocity is given as x dot is 1.2 feet per second. In this case, the only thing that you have to be worried, since we don't have any, like I didn't set this up with any coordinate system, is that we, and I kind of messed this up, but we know this distance is like, hey, let's say that's just x naught, and at time, like the next time, does this distance get smaller? Yes. So that's kind of it's kind of a rule of differentiation, is that, you know, for any of these things, hey, like x as a function of time is like an initial x, but then plus the change in x, you know what I mean? So that's going to be dx dt. Cool. But in this case, if this is getting smaller, you know, dx dt must be a negative number, you know. So it's going to be either x naught minus dx dt, and we can say that, hey, dx dt, just maybe the absolute value of it's 1.2 feet per second. But this was the case where I got confused when I did the differentiation and I saw this x dot was velocity. I just plugged it in as 1.2, but we see that this is kind of a common, and I got to do this more, is just like, heck yeah. Just like, hey, what's h as a function of time? That's going to be h naught, the original h, maybe plus dx dt, the change in h. Or I'm sorry, dh dt. But we know that's just 0, and h doesn't change. So h as a function of t is just h naught. Sweet. And you could say h as a function of t is h naught to the t to the 0. But maybe you, yeah, you can do that. Hell yeah. And yeah, let's go over it. I think you can. See, that's the thing, is just like I don't want to box myself in when learning differentiation, because like, hey, if I can actually say this, that this is I don't know if I could though, because differentiate. Oh yeah, no, you can, because I was kind of confused myself, because if we have d dt of h naught t naught, like let's do this Like, let's do it like we're totally crazy. Like, this actually is a product. We just know that this is 2 feet. But this is, you know, it's still a product of 2. And t to the 0, that's just 1 anyway. So we have 2 times 1. We're taking the derivative of 2 times 1. But this kind of spells out the process where you're just like, yeah, you can, we're still going to turn this into the product rule. So we're going to have the first times the derivative of the second. Oh, sweet. Finally, we have a t there and a t there. Done with that. Plus the second. So we're going to go t naught times the derivative of the first. D dt of h naught. Well, h naught doesn't have a t in it. So let's go d dh of h naught. And then we're going to go d h dh naught dt. So so yeah, dh, that's just going to be 1, you know what I mean? Or this is actually getting nonsensical, because you're going to have like 0 divided by 0. You're going to have no change there. Let's see. Oh no, we might be good. I mean, how I did it below, so we have t naught dh to the 1 dh, and then we had dh dt. I said this was t naught. This was going to be, bring down the 1. This goes h to the 0. That's the derivative of h to the 1. And obviously this is just 1, 1. This is 1. And then dh dt, this is going to be your h dot. And yeah, h isn't changing. So h at time 1 second is the same as h at time 0 second. It's always the same. In this problem, this height is always the same. So this change, this is going to be 0. So you're going to 0 over any number of time is 0. So that's where that term just becomes 0. So let's go back to this term. We're going to have that initial h naught, and then we're going to differentiate this, and then so when we differentiate with respect to time, like t naught, or if we differentiate with respect to x naught, you know, using the power rule, the 0 comes down, and then it goes x to the negative 1. But you know, so we're going to have 0 divided by x, but 0, you know, divided by any number is 0. So this term also becomes 0. So that was just to prove that when you have the derivative with respect to time of a constant, whether you put that constant as t to the 0 or just leave it as a constant, this is going to be 0. So we've all heard that. Hey, it's a constant, we're taking the derivative of it, it's 0. But just the simple thing, derivative of a constant dt says, hey, if it would be like the derivative of number 2 with respect to time. Like, number 2 was the same yesterday as it is today. The number 2 will be the same tomorrow. You know, so the change in the number 2 is 0. There's no change. 2 minus 2 is 0. It will never change, divided by the time. You know, it could be any amount of time, any number. But yes, a constant, the change of a constant with respect to time or angle or anything. You could change anything about the parameters, and a constant will always be constant. So that's why the derivative is 0. Alright, hell yeah. So this wasn't the easiest way to do this problem. I think it's easier to do cotangent, or is that right? I'll have to look that up and figure out why, but maybe we'll do that next. But anyway, so we're going to throw this in for x. So we're going to have x squared is h squared cosine squared sine squared theta. So hopefully that was obvious. If we square this, this is a product and a quotient. This squared can apply to everything. You know what I mean? So that's kind of what we do. And Man, I just want to do this on this one sheet. So we're going to have theta dot, which is angular velocity. It's going to be negative h. The velocity x dot. We're gonna have cosine squared. I guess I'm just gonna write it. Cosine squared theta right there, divided by h squared. Cosine squared theta divided by sine squared theta. So that's that x squared term. I just put it right there. So now we can cancel some things out. This h cancels with one of those h's. These cosines cancel, and then the sine goes to the top. So we're going to have x dot sine squared theta divided by h. All right, hell yeah. And let's see if that actually, let's see if we can plug that into our equation. Or we're going to say this velocity. So we're going to say x dot is that velocity of A is equal to negative 0.12. That's the only thing you have to worry about is that negative sign. But anyway, so we're going to have negative 1.2 feet per second. We're going to have sine squared. We're just going to choose that angle of 30 degrees. So that's going to be 0.5 squared. That's going to be 0.25. That term right there is going to be 0.25. It's always good if you can do some of these in your head before putting them in your calculator. It's always useful. This is going to be divided by 2. So we're going to have 1/4 times 1/2. That's dividing by 2. So it's going to be 1/8. Did I get that right? Hell yeah. I don't know. Maybe I feel like I messed this up. But maybe negative 1.2 divided by 8. Yeah, hell yeah. And we get that. So we get that change in angle of negative point. Oh. My bad. I totally lost this negative. This negative sign right here I lost. It should be right here. So the equation is going to be, this. So we're going to have negative 1.2 sine 30 squared divided by 2. So there you go. So negative 1.2 sine 30 squared divided by 2. And so we do get a positive, because that's the most important thing about these. Just make sure you negative and positives. When this goes like this, our angle gets bigger, so you get a bigger angle there. All right, hell yeah. And that number comes out to be 0.15 radians per second. Now let's go back to this equation. Like, did this... man. It's like, did this equation not work? I mean, we got it to here. We set up the problem and we differentiated. It just had more variables in it. It's just like, well, what gives? You know, shouldn't that work? And so sure, we're gonna throw that in. So we're gonna have negative 2 times negative 1.2 for the velocity times cosine of 30 squared. And then we're going to divide by x squared. Well, but here's where you have to have, hey, if we throw in theta is equal to 30 degrees, the only, like, that comes down to the principle of these, of what I was talking about. If I have a ratio of sine, cosine, or tangent, it defines the angle. It doesn't define the lengths per se, but it definitely defines the angle of that triangle if I know the ratios of those. But here, I know h is constant, and then I know my angle. So I also know this value of x. So if so this derivative is useful, but you just have to, if I'm going to throw in 30, I have to get the number of x that makes sense. You know, because if I throw in the angle of 15 degrees, well, this height doesn't change, and I still need to have 15 degrees. So this x definitely increases. But yeah, but we know that x for this problem is square root of 3 times 2, and we're going to square that. So we're going to have square root of 3 times 2, and then we're going to square it. And hell yeah, so we get the same number. So this video of doing differentiation, and this is kind of the first video I have done doing this, and I'll go over a lot more of the simple stuff. But yeah, I just wanted to rattle this out. So what we're going to do is, my camera's going to die. Alright, hell yeah. So we're gonna end the video with differentiating with respect to time and getting all these parameters with respect to time. But I definitely want to just go back and do that one just a lot faster so you can kind of see the process. So tangent theta, and let's do it in a different way, because we said, hey, if we do it cotangent theta, we're going to have, and this is good because we never differentiated tangent theta anyway. Differentiate cotangent theta, the x is on top, h is on the bottom. We're going to differentiate with respect to time. Again, that's going to be, if you can just do this visually, I'm going to differentiate, well, since this is kind of tough, differentiate cotangent, that's going to be cosine theta, sine theta. We're going to differentiate that. But don't forget about this d theta dt, which is just theta dot. And then, so how do we differentiate this? We use that quotient rule. You know, bottom d top minus top d bottom, all divided by the bottom squared. You know what I mean? It's a lot, but if you can memorize it or just do a lot of problems. And then the other thing is, like, so this one, all you need to know is the derivative of sine and derivative of cosine. And I guess let's take our time. So if you're going to do a sine graph, I mean, you can just do this. Hey, sine goes this way and cosine goes that way. You know, cosine starts at 1 and goes to 0. Sine starts at 0 and then goes up to 1. And it starts with a slope. The slope right here is 1. You know what I mean? Slope of 1. This slope right here is 0, and then it's negative. If you actually want to draw the graphs 100%, I would divvy these up into 3 chunks, 1, 2, 3, and this is going to be 30, 60, 90, or this is going to be 1.57, you know, because that's pi divided by 2. This is going to be 1, this is going to be 0.5, so that's in the radians. So 0.5 radians, 1 radian, 1.5 radians is about pi divided by 2. Hell yeah. And if you do that in thirds, then I would do this. I would do a straight line all the way up to 60, and then a flat line right there. And then just kind of curve it out. That literally is sine. And then cosine, same thing. 1, 2, 3. This same thing, 90, 60, 30. You're going to do the opposite. You're going to start to 30 flat, and then go all the way to 0. And then just smooth it out, and that's exactly cosine. Cosine of the angle, and then sine of the angle. Alright, booyah. So when we do this, it's going to be bottom d top, so that's sine theta times the derivative of cosine, derivative cosine. Oh, and then so because the slope is 1, when sine is 0, so right here, if I did sine of an angle of 0 degrees, I'm going to get 0. But the slope of that line is going to be 1. Slope is 1. So what equation, when I throw in 0, cosine of 0 gives me 1? Well, it's cosine. Hell yeah. And this is going to be a positive number. So the slope is a positive cosine theta. Now this, look at this. The slope is always negative. Besides like the very first, like the slope of cosine of 0, is going to be, the slope is going to be 0, but any other number is going to be a downward slope. So what, when we throw in 0, gives us 0? Sine of 0 angle is 0. And so if we're trying to, so if the slope is 0, what equation, when we throw in 0, gives us 0? It's going to be sine theta. And then it's going to be negative. So the derivative of cosine theta with respect to theta is negative sine theta. Hell yeah. So bottom d top is going to be negative sine theta minus top cosine theta d bottom. Derivative of sine. And that's why I just quickly do this. What's the derivative of sine? Slope of 1 is cosine. Cosine. And the slope of 1 means like, hey, at this 0 point, what equation gives me 1 when I throw in 0? Cosine. So we're going to have cosine theta. All divided. So we had bottom d top minus top d bottom, all divided by the bottom squared. And right here, you should say, hey, we have 2 cosines. And this is where you kind of have to factor. We're going to have negative sine squared theta minus cosine squared theta. Factor out a negative 1, and this becomes positive. And sine squared theta plus cosine squared theta is 1. So we're going to have, don't forget about that negative, but we're going to have, so the differentiation of this is negative 1 divided by sine squared theta is equal to, now if we come over here, does h change? No. So you can, that's the whole point of like bringing it in front of the differentiation. That's why I did the chain rule. You could even do the quotient rule of differentiation here. And we might as well because this is long as hell. So again, you have to use, and here, see, I even forgot. I did not differentiate with respect to time. I differentiated with respect to theta. So what I got right here was just this part. And I still have that theta dot. So I'm going to just throw it right in there. So we're going to have negative theta dot is equal to this side. If we use quotient rule here, we're going to have bottom d top minus top d bottom, all divided by the bottom squared. And you see, hey, we got to use that chain rule. This is t, this is x, this is t, this is h. So this becomes, yeah, let's work out. So just, I like using a ton of steps just to explain these processes. So this is going to be h dx of x, and then dx dt, minus x dh of h dh dt divided by h squared. And again, how did we do this? This is going to be h. This x is to the 1, so we're going to have x to the 0, bring down the 1. Sweet. So this is just 1. You know, and then dx dt is just going to be x dot. So we're going to have h x dot minus this. Yeah, this is the nonsensical part, but sure, h to the 1, derivative of it is going to bring down the 1, h to the 0. So that's just 1. Cool. But I mean, with, yeah, it's, I don't know. You know what I mean? Not really. This is probably nonsensical, what I'm doing right there. But hell yeah. So you're going to have negative x h dot. And we just know that h isn't changing, so this whole side goes to 0. But we're still using that quotient rule. And so we're going to have that divided by h squared. So hell yeah, this thing is just h dot, x dot, the velocity divided by h. Cool. So that whole thing was just like, oh, this, like differentiating this with respect to time is the same thing as, well, we know this is constant, so we're just going to say h, and now we need to differentiate with respect to x, but make sure we still have that dx dt. So this is going to be h, the x is just becomes a constant, or becomes 1, like a x to the 1. The 1 comes down, and then x goes to the 0, so that's 1. Cool. And then we have just x. We have h. Holy hell. And then, oh, sorry. This constant doesn't go upstairs. It just comes out as 1 over h. So this is 1 over h. So sorry about that. So this is 1 divided by h. So yeah, it's x dot divided by h. So that's kind of the simpler way to look at it. We did the quotient rule. That was pretty ridiculous. But I like doing that. It's the reason I did these quotient rules is how I kind of got a better understanding of differentiation, especially when it comes to chain rule. How like you can chain rule anything, and you should, just to show even with constants that like, okay, I get it. Because yeah, okay. Anyway, so we got that x dot divided by h. And hell yeah, so now we're going to bring the negative. And anytime we see how I did this -1 and then I just put it, see like this can confuse you. It can confuse you to like be like, oh, is this negative always stay? Hell no. You can just do -1 as a product of, oh damn it, my camera cut out, but we were basically there. So yeah, this -1 is a product. And to get it to the other side, I was just saying you just divide by -1, which, you know, dividing by -1 is the same thing as multiplying by -1. So it's really easy just to bring negatives from left to right. But I don't know. I've been making less errors by any time I have a negative, just do -1. Like, see this? Look, negative sine theta. I'm gonna mess up on that. So just make it -1 times sine theta, you know, and then cool. Anyway, so to get all this, I'm gonna try to isolate the angular velocity. That's always hard for me to say, angular velocity. Theta dot is going to be the negative to the other side. This velocity, which is x dot, sine squared theta goes upstairs divided by h. And hell yeah, so that's the same thing. So we're going to have negative times, the velocity is going to be negative, so negative 1.2. And then sine 30 squared. Whoop, whoop. Whoa. Oh, man. And then divided by 2 for this h. I didn't like that. Alright, and so we get that 0.15 radians per second. Okay, like I'm so ready for bed, but we're going to do this one more time, and we're going to do it with respect to time. So this is kind of a fascinating one, because what is this? If I say this x is a function of time, you know, and this h is a function of time, we already did that, and this was kind of the most important thing. It's just like, well, isn't x as a function of time? Well, at time 0, and this is kind of Newtonian. This is basically why differentiation, from my understanding, works so well. Because if it's like the classic, I use the example, if I see you at the grocery store, and then a couple hours later, kind of got off work, but then a couple hours later, I see you at the bar, I know that you, and you were just standing there looking at the shelves, and then at the bar, you were just sitting there drinking a beer. You know what I mean? Your velocity was 0 in both these times, and then this change in time passed. But because I know the grocery store is not in the same place as the bar, there was a distance here. You know, like I'll just do distance. And so, I know quite a bit. I know that you had to have some sort of velocity to get to that distance. And if you had velocity, you had to change your velocity, which means you had to have acceleration. So you've had to have positive acceleration, and if you had positive acceleration, I saw you at the bar not moving, you must have had negative acceleration at some point. You know, so just even from that, seeing something at one location and seeing something at another location, you know all this stuff. As long as you're not doing quantum physics, you know, and setting up some sort of experiments like that, there is a continuity of time. So hell yeah. So we're going to do this equation for t. Well, it's just going to be x naught, but now we need to, you know what I mean? We either need to add or subtract like a change in x. You know, so there you go. And I'm just going to do the positive change in x, but knowing that when we solve for this, this is going to be our initial x plus our x dot. You know, this is going to be our initial x plus our, and wait, what is this? This is going to be our, oh, do I have this right? Or do I have this wrong? Whoa, okay, so no, like I apologize about this. I have this wrong because the units on this would be meters per second and the units on this would be meters. So dimensionally I have this wrong. So yeah, how you need to have the change in x, change in t, but then you need to multiply it by a change in t. I don't know why. So scratch all those equations I wrote like this, because this would just be x naught plus the dx plus the change in x. And I don't know if that's going to help me or not. But yeah, I think it was useful for me to know, like, hey, this was that initial x, but then it was going to be minus, we have a velocity here, it was going to be minus this velocity times time. So for this problem, it was, you know, since this velocity is constant, and you can use the integration approach. I mean, definitely go back to dropping yourself off a cliff, jumping into water. Velocity is 0, acceleration is 9.8. The first thing you do in this problem is write the definition of acceleration. Definition of acceleration is change in velocity, change in time, and then you can write it as a derivative, dv dt. And this is a number. It's a constant, 9.8. You can separate variables, so dv stays here, 9.8. And you can even say this is t to the 0. That's helpful for me, dt, because now I can, like, oh, what am I integrating? You know, because when I was differentiating, I was just like, well, I don't see a variable for that. But so when we integrate both sides, this becomes velocity is 9.8. This goes t to the 0 plus 1 divided by 0 plus 1. That's going to be that, what is it? Power rule of integration. And yeah, it's just 9. Velocity is 9.8 t. Cool, t to the 1 divided by 1, 9.8 t, plus a constant. But at t is equal to 0, throw in 9.80 here. What's our velocity? Our velocity's got to be 0 anyway, so plus the constant 0. Anyway, so that's how you would get velocity. So you can do the same thing if, and we know if we integrate again, our position equation is 4.9 t squared, you know, plus the other stuff if we did have a constant there. But when our velocity is constant, let's write the definition for velocity. Velocity is dx dt. Sweet. And let's separate, and that's going to be equal to negative 1.2. And so when we separate variables, we're going to have dx is negative 1.2. We can do t to the 0, same thing, dt. We can say our position as a function of time. That's literally what this is. This is a function of time. So you can put that little thing right there. This is a function equation. And we're going to have negative 1.2 t. Sweet. Plus the constant. And in this case, hey, when time is 0, what's our initial position? Well, in this case, we do have an initial position, and this is going to be x naught. This is going to be square root of 3 times 2. So that literally, and this will be very helpful, especially, there's no difference in x compared to radians, you know. Radians goes to angular speed, goes to acceleration, just as x goes to velocity, goes to acceleration. All right, hell yeah, I'm about done. But so sweet. So we get this equation that x naught minus 1.2 t is our equation, and we know this minus 1.2 t. I mean, we can just say it's x naught plus velocity of a times t, and that's our equation. All right, so you can do this, you know, you can say, hey, this distance right here, that's why this is a little bit trickier. This distance right here is x naught, or I'm just going to, yeah, I guess I'll do that, x naught, and then velocity times time. So that is that distance. And so now when we write our equation, I guess I'll make this a little bit easier on myself. We're going to go cotangent of theta is equal to this x naught plus v of t divided by, I'm going to say this is just h. Well, and I wouldn't even write this because I just know that if I take what is this angle? The angle is, I mean, it's just, I'm just going to drop this down, but if I'm trying to find the angle and then differentiate that angle with respect to time, where I have everything as a function of time, see how this is now a function of time? And then this x naught is a constant, this velocity is a constant, and this is h is a constant. So there you go. I've set up these parameters where everything is a constant except this time value. And so what is theta? Theta is inverse cotangent of this ratio. X naught, so it's going to be adjacent over opposite. X naught v of t divided by h. Alright, hell yeah. And now I'm going to differentiate this with respect to time. And guess what? I can differentiate this with respect to time. But still, you still use chain rule. Because, like, this is a kind of a... I mean, just from the fact that this is complicated. If you look this up in a book, you would see the derivative with respect to u of cotangent negative 1 u. And u is kind of just like a catch-all to be like, hey, for the time being, let's just make this just kind of like a normal term. Like if it was just a variable like x. Because, and then if you differentiated x, you would just get 1. dx is 1. So keep that in mind. But yeah, if you look this up in the book, you're going to get negative 1 divided by 1 plus x squared. You can just memorize that. Cool. But this is the differentiation of this part. But to do this, you're going to have this, your u is going to be right here for your x. And then you're going to have du dx. So, and just to spell it out in words, cool. So just throw this in for your u. Let's do that, negative 1. I'm going to set this up as a product just like that. 1 plus, and then I'm just going to x naught plus v of t divided by h, and then I'm going to square that. Cool. But now we have to take the derivative of this. So the derivative of this, I mean, you can even spell this out. Just this is going to be x naught divided by h plus v of t divided by h. Well, this is a constant, so the derivative of the inside, but you can't do that either, because you still have something useful here. You know, so this is also another u substitution. You have u squared, and this stuff in here is not a constant. Just like the stuff in here was, if the stuff in here was a constant, you would still have to use u substitution as well. Yeah, I think you would. Yes, but anyway, but But yeah, so the derivative of this is going to be, the 2 comes down, so we're going to have 2, everything inside this box, x naught plus v of t divided by h, to the 1 power, and then differentiating what's inside this box. And that's where I was trying to get at. Inside this box is x naught divided by h plus v of t divided by h. And so we're just going to have just this. It's a v of h is a constant. Differentiating t just becomes 1, so it's just going to be VH. So it's going to be V divided by H. So that's, yeah, we didn't have to use the quotient rule. We didn't have to go bottom d top minus top d bottom. We could do that. Let's do that right now. You know what I mean? Might as well use the product rule and quotient rule just to show there's many different ways to get the answer. So bottom d top is H times V minus top d bottom, that's going to be 0 divided by the bottom squared, h squared. Hell yeah, look at that. So pretty fast we just get v divided by h. And so that's what we got. Alright, you know what I mean? Plenty of places for error on this one. But we did it. Alright, hell yeah, let's get back to it. And anytime I do it with the change in time, man, it's you know, you have to use the, typically you have to use the derivative of inverse cotangent or tangent, and it just gets, you know, you're dealing with the, it's kind of based on the Pythagorean theorem. That's why you have, like, you know, the stuff squared. But anyway, so we should be good to go here, and let's see if we, I don't know if I want to simplify too much. Sometimes it's just better just to throw this into your calculator. So we're going to have -1. We're going to have this 2. We're going to have, I better throw in square root of 3 times 2. That's going to be my x value. So let's get back to here. We're going to have x plus, now I need to, my alpha v. Okay, but my alpha v is negative, so negative alpha v stored as alpha v. Sweet. And then alpha h, so 2 stored as alpha h. And then time is just 0. You know what I mean? So I'm just going to, and if we know time is 0, I'm not going to throw that in my calculator. I'm just going to, you know, kind of skip those. So we're going to have -1, 2. We're going to, so this just becomes x. This is 0, so it's x divided by h. Whoops. And then this is going to be alpha v divided by h. So v divided by h. Okay, we need to divide this. So we're going to divide by 1 plus, now this is going to be x divided by h squared, because that's also 0, x divided by h squared. And I think we're done. And hell yeah, we got the wrong answer. So let's check our errors. Alright, hell yeah, this was an easier error. Well, I don't know what errors are easy and what errors aren't. Sometimes they're a pain in the butt. But I'm glad we started the video by getting the actual answers, you know, from a process that's just kind of the 3-point method. Because then when you do this, you get better at, like, because my error was here. So this was the differentiation of cotangent. -1 divided by 1 plus u squared. And then it's du dx. It's the derivative of what's inside the u. So the u all along was just this. It's so the derivative, yeah, so it wasn't the derivative of this, it was the derivative of what's inside. So the 2 goes away, what's inside goes away. And I was wondering about that. It just seemed a little bit complex. But yeah, it's just this v divided by h. So hell yeah. So let's bring this up again. And I guess let's just redo it. So we got -1 divided by, we'll do this first, 1 plus x divided by alpha h. And then we're going to square that. Alright, so we got the right parentheses here. Now we're going to move up to the top, and we got alpha v divided by alpha h. Alright, hell yeah. So we get that answer of 0.15, and that was omega or theta dot. Okay, so hopefully this was a 3-hour video. I don't know, I was trying to shoot for at least 2 hours, but you know, of going over the basics from square one, introducing trigonometry, and then introducing differentiation when it comes to trigonometry, because that's all anyone wants to know. And we just set it up 2 different ways, but we set it up in the kind of the most important 2 different ways. One was an equation that didn't involve time. It was just, hey, this angular speed is just based on this velocity, but it's based on that angle. You know what I mean? Sure, this angle is going to change, and if we can, whatever angle we're going to calculate this thing to be, we know and because of that velocity, we know it's angular rotation, angular velocity. But maybe you want to set up the experiment with a stopwatch right here, and you're not going to be able to calculate angle. What you can calculate really easily is just time. So if you set up the experiment, you know, with as a function of time, you can do the same thing. And so that's what we did. And that's why you had to get theta isolated and everything else over here in terms of time, because when you differentiate theta with respect to time, then you just get that theta dot. D theta dt is theta dot, is omega, is angular velocity, and you don't get that extra, you don't have to use chain rule, because when you do chain rule, sure, you get theta dot, d theta dt, omega, all the same thing for angular velocity, but you'll always have some sort of, you know, function of the angle still in there. And so so this is true to form, where you get just a function of time. This equation right here, you have you have velocity, that's a constant, height's a constant, this initial position of that value, that's a constant, and then you have that function of time. Okay, hell yeah. So we did it. And all we did was the first derivative. You know what I mean? Once you get here, then, you know, just like the one with time where you get theta all alone, sure, now you can differentiate with respect to time on this side, differentiate with respect to time on this side, and then you'll get theta dot dot. Or, yeah, theta dot dot. That's alpha. That's angular acceleration. That's what they want to find in this problem. But it's the same process. You know what I mean? Hey, we have a product here. We have this, we have that, and we have h. You know, h is a constant, cool. Now, even right here, you can point out that the velocity is a constant. So you can take that outside of the differentiation. We can explain that. So now you're just differentiating sine squared theta, yeah, I guess, yeah, let's spend at least 5 minutes on that. Yeah, because you kind of want to know, like, what's the full picture. So once I get this equation for theta is negative x dot sine squared theta divided by h, you know what I mean? Now what gives? Well, we're gonna differentiate both sides with respect to time, but we're gonna run into that same problem. None of these are, you know, with respect to time. I mean, well, this one is respect to time, but this one's not. And we just said, hey, we identified that these are constants, so let's bring them outside. Even though that's kind of an advanced maneuver. Who knows if there might be acceleration of this, but just by definition it says, hey, this is moving at a constant speed. If you didn't know, you would have to differentiate this with respect to time, and you would have a product. You like, sure, this could be a constant. The negative can be a constant. -1 can come outside, but you would have 2 terms here. So you'd have to take the first times the derivative of the second plus the second times the derivative of the first. But since you know these are constants, we can take them outside the so we're going to have theta dot over here, and outside the differential equation. So we're going to have negative x dot divided by h outside. And now for this, you'd have to differentiate with respect to theta again. you can't differentiate with respect to time. So now we'll have d theta dt. That is the chain rule. This becomes theta dot. So keep that in mind. In all the problems, this is its own thing, and we already know theta dot. So this theta dot is this that we can throw in there at the end. So keep that in mind. So now this is going to be theta dot dot is doing all this. And the differentiation of sine squared theta, sure, you're going to use the not quotient. What's the opposite of a quotient where you have a product? Yeah, product rule. Is that what it's called? I'm losing my brain right now. But anyway, it's going to be first times the derivative of the second. Quickly draw a sine graph, draw a cosine graph. We just need to do a sine graph. So the derivative of sine is cosine. So we're going to have first times the second. So that's going to be sine theta cosine theta plus the second times the derivative of the first, sine theta cosine theta. So this is just going to add up to 2 sine theta cosine theta. And booyah. So the double dot dot is going to be negative x dot divided by h times 2 sine theta cosine theta. And then we're going to have this theta dot. Theta dot, let's just throw it in, you know what I mean, is going to be negative x h sine squared theta. Negative x dot sine squared theta. Sweet. And so we're going to have theta double dot is going to be, and then the negatives are going to, so we're going to have negative x times negative x. Okay, the negative goes away for sure. So we're going to have theta dot squared divided by h squared sine cubed theta cosine theta. And let's throw this all into our calculator. So we're going to basically have negative 1.2, but we're squaring it, divided by 2 sine 30 cubed, sorry if I said squared, cosine 30. Booyah. So we're going to have 1.2 squared divided by 2 sine 30 cubed. Bummer. Sine 30 cubed, and then cosine 30. And I'm in degrees. Hell yeah. So there you go, 0.0779. And the only issue was I wasn't able to get the derivative of this first try. So why do a 3-hour video and not go this extra mile? So I'm going to rewrite this, and we're going to try to take the derivative of this, because this literally is theta dot right there. We took the, if you take the inverse, if you take the cotangent, inverse cotangent of this, we isolate theta. You get the cotangent of that, and that's what we took the derivative of, and then that gives us the angular velocity. So let's rewrite this equation, and friggin' A, let's do it. Alright, hell yeah. I feel like I'm going to mess this up, but as long as you follow the rules, you know what I mean, you should be good to go. So we're going to have ddt down here, and I mean, there's a couple ways to do this. You could take this whole thing and move it upstairs, and then you could do the product rule of integration. Else you're going to do the quotient rule, which kind of makes it harder. I think we should do the quotient rule and then back it up with the product rule. Now I think we should do the product rule first. So product rule says, hey, get everything upstairs as a product. And so now we're going to have this whole thing upstairs. 1 plus, now I'm going to take it to the negative 1, so don't worry. Alright, so this to the negative 1, cool. So now, but these are constants, so when we take the derivative with respect to time, these can come outside over here, and now we're just differentiating this. So to do that, the negative 1 comes down. We're going to have everything in the box to the negative 2. And now you can see that, oh, if I used the quotient rule, I would have squared all this to be at the end anyway. It would be bottom d top minus top d bottom, all divided by the bottom square. So you can see kind of how they're related. Okay, but now I need to take the, I need to differentiate, I need to multiply this by the differential of the inside. And so that is going to be also a product rule. So I get used to, this is kind of a cool tip. So I'm going to like differentiating this is 0. But now I need to differentiate that. I bring the 2 down, and then I'm going to still have to multiply by all this on the inside. Take the power to the 1. I'll just do that. And now I need to take the, multiply it by the differential of the inside. And that's going to be just v. Well, v over h. Yeah, can't mess that up because it's x naught over h plus v over h. Alright, hell yeah, we're back. Alright, so, yeah, we brought the 2 down, took this to the 1 power, but then you got to differentiate on the inside, and, yeah, don't mess that up, because it could be a quotient rule, you know what I mean? But we can take it into 2 different things, x naught over h, v of t over h. This differentiation is 0 because it's a constant. This is a function of time, you know, t to the 1, so that's just going to pop out that vh. And technically, this should be the answer, you know what I mean? So I guess, should we write it? And hopefully this is theta double dot. 1 plus just all this stuff. It's awful. Just a lot of places to mess up too, to the negative 2. X naught plus v of t. But I've done this a few times where if you do this, like come up with different symbols, so you don't have to write just thousands of things thousands of times over, it's going to be way easier. Alright, so let's throw this into our calculator and just pray that we get the right answer. 1 plus x. This is just going to be x divided by h, because that t is 0. Because we're... the cool thing is that, hey, we have an equation for this as a function of any time starting at 30 degrees. Or, yeah, starting at 30. You know, if you wanted to start at a different angle, you would have to throw in a different x naught. And that's about it. You know, you can change up all the parameters. But anyway, alpha h. And you can get the acceleration at any time. You can figure out how much this is accelerating, you know, by throwing in that time value. We just want to know at time 0, so at that 30 degrees, that's kind of the balance, the kind of the check on this. So we're gonna, holy Toledo, probably already making mistakes. Oh, I see. If I go this to the 2, it messes it up. Yeah, I was kind of doing that today. So I can just do that. Okay. Parentheses. Alright, this to the negative 2. Got it. 2. I'm just going to do in parentheses just so everything kind of looks the same. X divided. This is 0, so it's just x divided by h. And then we have alpha v divided by alpha h. Holy hell. Come on, come on. Nah, it didn't do it. Alright, I'm going to take... no, we got to do this on camera. You got to find your errors, man. So, yeah. And I think... yeah, I'm trying to get better at just like, well, did you just mess up something? You know, so we'll just pull up the equation. Might have been something small. We'll do something small to like the something big. So we got negative 1. Oh, you know what? Oh, hell yeah. So I didn't do this part at all, because we'll have this square. See, we ended up with a VH. Yeah. So I've done this a bunch, but yeah, you'll get these terms repeated. So remember that I tried to factor this constant out at the beginning. I didn't do that right here. I just said negative 1. We should have another v to the h right here, or I can just square it over here. So that was it. You know what I mean? I'm almost guaranteed that was it. Put a little square here. I'm getting way better at finding errors and booyah. We're off by a negative sign, but I hardly give a care. Wonder why we're off by a negative. Alpha V, yeah. Oh, that's interesting. Oh yeah, duh. Oh, no. Another error. Yeah, this -1 wasn't this -1 anyway. It was, I took this whole thing upstairs, and then I said, hey, the differential of this is bring down the -1, take this to the -2. But then I totally forgot about those three terms. So we have a negative and then a v to the h. I added the v to the h by squaring this, and then I need to add another negative just by turning that positive. So hell yeah. And we are done. Whew. So turn that into a positive. Booyah. And we get the angular acceleration. And the cool thing about this equation is you're almost guaranteed, unless I kind of messed up this little term, in any sort of way, because this term just became 0 and everything. This is an equation that will work at any time from here to here. And then the other thing that I'm not going to do with this video is if you have the original derivative, the original equation for angle was arc cotangent, inverse cotangent of that initial dimension there plus velocity times t divided by h. And if you differentiated with respect to time and you threw this into as a d dt. If you threw this into differential, the derivative calculator online, it's so good. You can take this. You can take two derivatives. You can take as many derivatives as you want, but take two derivatives of it and get the theta dot and theta double dot just like that. Now the trick is how to set these up correctly, because if you don't have this term set up correctly, obviously you're not going to get the right answer. But still, even on that, what you want to do is that 3-point method and to figure out just from geometry how much this is changing. And so those are my tips for how to do differential calculus and set up problems using differentiation. And what I'm learning is like, holy Toledo, once you figure out the tips on differentiating, it seems just like the gold standard. You wouldn't want to do it any other way. But I still like to do it. I like to use the 3-point method the most. Be like, hey, let's just change it just a tiny bit. That'll give you the exact answer, just so well and so easy. Like, look at all these steps you need to go through just to get that. So that's my first way to double check. That is my first check and double check on the answer. That's the answer that I use to make to clean up errors. Because if you do this process and you just get like 0.25, how would you know that's even wrong? You know what I mean? It would be almost impossible to find errors if you didn't have any way to judge like what the answer would be. And that's why I didn't spend a lot of time. We talked about, what the derivatives are. You know what I mean? So if I have cotangent, here's my angle. Cotangent is this adjacent divided by this. So if I say this is A and this is B, it's the ratio between A and B. Anyway, and whatever that ratio is, the cotangent means, hey, it pops out this angle. You know what I mean? So if I say this is 4 and this is 2, that's going to be a ratio of 2. And then so the inverse cotangent of 2 says that this ratio between these are 4 and 2 is 2. And that's going to be the angle. So if I go 1, 2, 3, 4, and then up 2, that's the angle. Whatever angle that is, about 30 degrees, is... and a little bit less, is going to be that's going to be the cotangent part. Now the differential part is like, hey, as a function of time, because I know this thing is moving this way, and this dimension is getting shorter as a function of time. So that's how we do that. And anyway. And you could do it manually. I need to do that more. Be like, hey, do this, figure out what the cotangent is at time 0, and then the cotangent at time 1 second, or 1/10 of a second, or 100th or 1,000th of a second. And then I can find the difference in this, and then divide it by that change in time. Whether I chose a 1 second, it's just 1, but it's not going to give you a very accurate answer. Choose 1,000th of a second, you're just guaranteed to get 100% accurate. Alright, so hell yeah. So I think I'm done with this video. I need to go to bed, and thanks for joining me, and that's the video.